Right, so we want to look at inverse functions, and this is 1.6. And if you remember when we looked at section 1.4, we talked about the reflections on Monday. I showed you that other reflection, the reflection across the line y equals x. Okay, the reflection across the line y equals x, and we said that this wasn't one of our standard transformations, but that we were going to use it later. Well, here we are, okay? We're going to be using this for the inverse function. We'll get to that in a moment, but let's first of all define what an inverse function is. You guys back in pre-algebra learned about inverse operations, okay? Those are called inverse operations because they give you the identity. In other words, if you were multiplying and dividing, the identity was 1. Okay? So when you multiplied by 2, and then you took that result and you divided by 2, you got back to the original value. We started with an x. We end with an x, and that's because multiplying by 2 and dividing by 2 are inverse operations. We could also look at those in the sense of inverse functions, okay? Inverse functions are functions, let's say I have f of x, and it's 2x, and I have g of x, and that's x over 2, multiplying by 2 and dividing by 2. Okay? Now, why are those inverse functions? Let's look at our domain. Okay? It says inverse functions, two functions are inverse functions if f of g of x equals x, and it's important because it's got to work both ways, g of f of x equals x. All right? So watch this. If I take, let me erase this. If I take f of g of x, f of x over 2, all right? F of x is 2x, so I have 2 times x over 2, right? Well, what does that equal? X. All right? If I did g of f of x, well, f of x is 2x. That means g of x is x over 2, so I have a 2x over 2. And what does that equal? X. So guess what? We just proved that the function 2x and the function x over 2 are inverses. Because when we compose them together in either order, we end up with x. Okay? Now, one piece of notation that we can see is this little -1 here. One thing you have to be careful about is to understand the context that you're looking at. That -1 is talking about an inverse function. It's not talking about 1 over something. Okay? It's not a reciprocal. It's not an exponent. It's actual notation for an inverse. Now, what this means is we could call, since f of x and g of x are inverse functions, we could call g of x f inverse of x. Okay?
Or vice versa.
Or, yeah, or we could call this g inverse of x if you wanted to. Okay? Usually we just pick one or the other. So, we'll do that. But yeah, you could do either way. Okay? They're inverses of each other. Now look at what happens. Just to kind of picture this. Here's our domain of f, this set of numbers. And the function f takes that value of x and it gives us something in its range. D of f, that's the domain of f, R of f, that's the range of f. Okay? One thing you have to understand is that inverse functions, the range of one is the domain of the other. Okay? See how up here I have written that this is the range of f, but when we're looking at function g, the inverse, it's going to take this value, so it's the domain now of g, and when we evaluate it, we get x. Okay, it takes us back where we started. Okay. By the way, another place that all of you have seen this notation for inverse is on your calculator. Okay? If you look at your calculator, above sine, cosine, and tangent, you have sine -1, cosine -1, tangent -1. Okay? That little -1 is not the reciprocal of sine, it's your inverse. Okay? So you've all seen that notation a little bit, you just may not have recognized it. Mm-hmm.
So let's just say you have a parabola, and then you find the inverse of that. Wouldn't it be like sideways, and then wouldn't it not be a function anymore?
You're right, and that's actually what we're going to answer right now. Okay?
Oh my god,
You like read my mind. So, all right. So here's the question: does a function have an inverse function? Now, theoretically, we could do the mathematics to do an inverse either way. Okay, but we're not always guaranteed that inverse, or I should just say that reflection across the line y equals x, will actually be a function. And the parabola is a perfect example of this. Here we have our parent function of x squared. If I reflect that across the line y equals x, that's how we will find the inverses of different functions. Okay? However, you'll notice the result here is not a function. It fails the vertical line test. Okay? Let's just there. So what we have to do in order to look at x squared and the square root of x as inverses, we would have to limit the domain here. Okay? Because see, if I tried this, if I tried f of -2, -2 squared is positive 4. But then if I try the inverse square root, the square root of 4 could give me two different possible answers. So you see here, this function here is not necessarily going to take me back to exactly where I started. It gives me two options, and one of them happens to be where I started, but that's not good enough to have an inverse function. Okay? So, how do we work with this? Or how do we know that we have an inverse function? We have to have a function that is what's known as one-to-one. Okay? One-to-one. A one-to-one function is a function where every element of the range has only one element of the domain that's mapped to it. Okay? Now notice with this parabola. Okay? For this parabola here, we have this value in the range that's 4. See this? Here in the range, y equals 4. Right? But there are two different values of x that get mapped to 4. Positive 2 gets mapped to 4 by f, and negative 2 gets mapped to 4 by f. Okay? So since there are two different x values that both equal 4, this function would not be one-to-one. And as you can see how I drew this, the easy way to see this is the horizontal line test. Just like we had a vertical line test to see if things were functions, we can use a horizontal line test to tell whether its reflection across the line y equals x will be an inverse function. Okay? So, if, like in this case, a horizontal line crosses your graph in more than one place, it's not one-to-one. Okay? Not 1, 2, 1. Okay? Does that make sense?
Yes.
So this is why we would have to define f a little bit differently. Maybe we would say f of x equals x squared, but what could we do to make that one-to-one?
X is either greater than or equal to 0 or less than or equal to 0.
Yeah, we would have to limit the domain. Okay? So we could say, all right, f of x is x squared, and x is greater than or equal to 0, then that eliminates that second possibility. Okay? And that makes it just a one-to-one. All right? So that would have an inverse, but the original function would not. Okay? All right, so let's look at how we would actually find this inverse. What did we say happened to every point when we reflect something across the line y equals x? The x's and y's switch. So guess how we find the inverse?
How?
We switch the x's and y's.
No.
Okay? So here's what we do. All right? Here we have f of x, which we could say is a y. We're going to put a y in place of the x, or actually I could even put f inverse of x. So 3 times that plus 7 is going to equal x. All right? If you want to use y, you're welcome to use y. Okay? Now all I have to do is solve to get my inverse function. So I would subtract 7, and then I would divide by 3, and I get my inverse function, not prime, not in calculus. Inverse function is x minus 7 over 3. Okay? Let's try over here, g. Okay? I'm going to put an x over here. 5 plus the cube root of, we want to find g inverse of x, right? So how would I solve this for g inverse of x?
Subtract 5 and then you...
Okay, subtract 5 first, and now I have the cube root of g inverse of x. And now what?
Cube it.
We cube it. X minus 5 cubed is our g inverse. Okay? We didn't get to the last example, but I think you guys get the idea. Alright? Alright. Any final questions before you go? Alright, we'll see you tomorrow then. Have a great day.